Okay, a very good morning, everyone. In this talk, I'm going to share my latest research work that could be related to the topic of this symposium, Resilient City. The first topic is the fluid pressurization induced failure of the rock fractures. And the other is a mechanical response of frozen fractured rock. These works are carried out by my research staff and PhD students in my group at NTU Singapore, and supported by, as you can see, various government agencies in Singapore, such as the National Research Foundation and the Ministry of Education. In recent years, we can see frequent extreme weather due to the climate change. You may remember the Zhengzhou flood this summer. 12 people have died after rainfall flooded groundwater railway tunnels and leaving the passengers trapped inside the rising water. And you may also experience extremely cold winter at the frozen temperatures. On the right, you can see this is a frozen park in Texas in the United States. From the two examples, I want to talk about the impact of the extreme conditions in the mechanical behaviors of fractured rocks. I think this topic is very few people has been looking to this topic. As the reason is the climate change. We can see the change of weather, change of temperature, but very few evidence showing that the change of the change in the rock mass. But if you look at water, okay, water can be the medium, link up the change of the rock mass with the temperature change or the climate change. So the first example is about the stability of rock fractures with abnormal high fluid pressure inside the rock. We know hydrostatic condition. Okay, the fluid pressure increases linearly with the depth. However, the groundwater flow and the rainwater downflow can make the fluid overpressurized locally. The fluid pressure is close to the principal stresses, as you can see here. So promote the instability of the rock slopes and the water inrush into the tunnel. And traditionally, we use this molecular model to describe the fluid pressurization on rock fractures. When you increase the fluid pressure, it could decrease the effective normal stress and drive the circle from the left towards the right. The model assumes the uniform pressure distribution of on the fracture. But sometimes, if you have heavy rains, you have high pressure on the ground, you may have the fluid pressure suddenly increase, making the fluid pressure non-uniform on the fracture. So in this case, how can we consider the instability of the fractures if the water pressure is not uniform inside the fracture? So we design the shear flow setup. Here we have a rock core sample. We cut the sample with a saw cut fracture 30 degrees to the core axis. We apply the normal stress and the shear stress on the inclined plane of the fracture. In this test, we first determine the shear strength. We induce the slip, then we can measure the maximum shear stress as a strength. Then after that, we decrease the shear stress to 80% of the shear strength to simulate the critical stress state of the fracture. Then after that, we inject the fluid into the fracture through the inlet borehole and monitor the pressure on the other side of the fracture. So we will see the fluid pressure distribution along the fracture, either uniform or non-uniform. The next, let's look at the results. Here we summarize the results. You see the dashed line. This is the failure envelope of the molecular model. And when the effective normal stress is small and the injection rate is low, then we can see the points, failure points, are very almost on the failure envelope. That is what we learned about the molecular model. However, if you have the effective normal stress very large and the injection rate is very high, the failure point can overshoot the failure envelope, showing that the failure envelope or the molecular model is not valid because in this case, the fluid pressure is non-uniform on the fracture. So this cannot fulfill the assumption of this molecular model. So in this case, how can we deal with the non-uniform fluid pressure on the fracture? How we can consider this case in a engineering applications? And first, we need to understand the real case of the fluid pressure inside the fracture. We cannot see it because this test is in a hexagon cell. So we use a COMSOL software to virtualize the fluid pressure distribution on the rock fractures on the low and high effective normal stress. For the left case, you see the fluid pressure is nearly uniform. This case is uniform because the fluid pressure is you see a very small difference. In this case, we derived the fluid pressure along the axis of the fracture, that is this line, now, which is very close to the line, the fluid pressure predicted by the molecular model. This is a fluid pressure uniform on the fracture. On the right, if you look at the other case, when the fluid pressure is very non-uniform on the fracture, the pressure not equal to the to that predicted by the molecular model. Okay, so from those two cases, we can see the fluid pressure is not uniform on the fracture. The molecular model cannot be used anymore. So how can we consider the impact on the influence on the engineering case? So here we estimate the factor of the safety for three cases. You see the three lines. One is this line, the green color. This is a uniform fluid pressure distribution on the fracture. And second case, the red line here is the linear fluid pressure distribution. And this is a blue line. This is a non-uniform or non-linear fluid pressure distribution. So we have the three types of the fluid pressure distribution on the fracture. Then we're trying to derive the factor of safety to see what is the impact of the fluid pressure distribution on the factor of safety. Here we define the curvature for the three cases, as well as P1 and PU, which is the fluid pressure, as well as a uniform pressure required for fracture failure. And this is the results. Let's look at it. For a constant initial fluid pressure, we can see the factor of safety increases as the pressure ratio P1 over PU increases, and the curvature alpha decreases. And here are the three cases representing different initial factor of safety. But for all the cases, we can see that a more significant non-uniform fluid pressure can result a higher factor of safety. So if you, in your engineering applications, if you see the fluid pressure is very high on one side of fracture, you cannot use a traditional factor of safety to predict the stability of the rock. You should consider the fluid pressure enlarge the factor of safety in this case. Okay, so this is the first case. And second one, let's look at the mechanical response of a frozen fractured rock. This image, I think, is very common in a cold area. If you go out, especially in those months, in the winter on the north side of China, you will see this kind of rock mass with a closed fracture, right? You can identify many features from this image. The gouge-filled fracture, the ice-filled fracture, the fracture network, fracture spacing, right? Many features, you can see it. And if you're combining all the features together, you will see it's very complicated to predict the mechanical behaviors of the rock mass. So in our study, we try to combine the many approaches, such as laboratory experiments, numerical simulation, and machine learning to predict the mechanical behaviors of the fractured frozen rock. So we first conduct the uniaxial compression test, a very simple test, on the intact rock sample and the frozen rock sample with ice-filled fracture. So here you see those fractures actually filled with ice. We put into a fridge. After that, we take it out for the uniaxial compression test. And we use those test results to validate the PFC model. We create the PFC model with rock materials at 0 degree temperature, as well as ice fractures. And we consider different parameters in this fracture. We consider the inclination of the ice layer, the spacing of the fractures, and also other parameters. Okay. The first, we use experimental results to validate the numerical model. We performed about 200 numerical simulations. And then next, we put those results from numerical simulations to train and validate the machine learning model. Here we have we use a random forest model to simulate or to predict the mechanical behaviors of the frozen fractal rock. We actually use tried with many machine learning algorithms, such as neural networks, support vector machines. And finally, we found that the random forest is the best to perform or to predict the mechanical behaviors of the fracture network. And here we use the 5 parameters as the input: persistent factors, inclined fracture, rock layer, ice layer, the thickness of the ice layer, the fracture number, fracture spacing. The persistent factor is defined as the sum of the fracture trace over the total length of the skyline. Right, we have the other parameters together as inputs, and use uniaxial compressive strength and Young's modulus as the outputs. And this is the flowchart for the random forest model. And we have 200 numerical simulation results, and we're using 75% to train the model and 25% to validate this model. And this is the results showing that the comparison between the random forest prediction and the PFC simulation results in terms of the uniaxial compressive strength and the Young's modulus. And you can see the prediction results is quite good based on the R square, root mean square deviation, and the mean absolute percentage errors. And we also use our prediction results and the simulation results to compare with some other existing models in the literature, such as Ramamosi model, which is a kind of empirical model to predict the strength of the rock. And you can see the model expressed in these equations. And we can also have a good agreement between this model and our machine learning model. Finally, we perform the sensitivity analysis. We find that on the right, the persistent factor is very important in the prediction of Young's modulus, and the inclination angle is critical in the prediction of the uniaxial compressive strength. So that is topics I want to share with you. Here is just some small effort to address rock mass behaviors modified by climate change in terms of high water, low temperature. Probably in the future, we will see more factors that can affect the behaviors of the rocks. And the influence on the rock mass, as I mentioned just now, could be very invisible in the current stage because we just see the temperature change, we see the rainwater, but we cannot see the effects on rock mass. But if you look at water, water can be a medium to link up the climate change and the rock mass behaviors. That is a point that we could consider for our fundamental studies as well as the engineering applications. Okay, thank you.